Okay, welcome to Origin Seminar for December 2nd, 2024. Thank you all for coming. Today we have Tatsuya Akiba. He's a final year PhD candidate currently on the postdoc job market. He is in the astrophysics department at the University of Colorado Boulder, working primarily with Anne-Marie Madigan. Tatsuya is interested in gravitational dynamics in a variety of astrophysical contexts, from exoplanetesimals around white dwarfs to stars around supermassive black holes. And today he will be telling us about hungry white dwarfs, and about how white dwarf cannibalization of nearby planets can give us insights into solar system composition. So take it away.
Awesome. Thank you so much, Allison, and thank you for being here, and to the Zoom people, thank you for being here as well. Like Allison mentioned, I'm a final year PhD candidate, primarily working with Anne-Marie Madigan. She'll actually give the theory astrophysics colloquium later today, so I'm also advertising her talk there as well. Today, so I'm primarily a dynamicist, and I study how astrophysical objects interact with each other through gravity in a variety of different contexts. Today, specifically, I wanted to talk about white dwarfs as sort of the central object that is dominating the gravitational field, and exoplanetesimals around them, and how they're going to torque each other through gravity, and cool things like that. I wanted to mention that this work was done in collaboration with an undergrad student, Salem McIntyre, at Colorado Boulder as well, alongside Henry. Okay. So let me just start with what are white dwarfs. So am I talking about this is my cat Sora pictured here, but we're talking about astrophysical white dwarfs today. So he is also kind of a hungry white dwarf at home. But anyway, okay. So white dwarfs, you have probably seen this diagram before that is showing the different stages of stellar evolution here. And so the main branch that happens right at the beginning is how massive the star is. And so what I want to mention is that these low to medium mass stars, stars that are less than about 8 solar masses when they're on the main sequence, will sort of follow this top branch. And so as you're on the main sequence and you run out of hydrogen in the core, you turn into a giant star, and eventually you go through the various giant phases. And then the final sort of stage is something called the asymptotic giant branch. You start to sort of lose mass to the surrounding. And then the very final stage is sort of a white dwarf that remains. So the core of the star sort of, due to gravity, turns into a dense ball or there's much debate as far as whether that's a star or not. But a white dwarf is born at the very end of this low mass main sequence stage. Okay, and so on the other hand, if you have a high mass star, you go through a red supergiant phase and then a supernova. And depending on the mass, once again, you either turn into a neutron star or a stellar mass black hole. But today I'm going to focus on the top branch here, and specifically what happens to white dwarfs and the surrounding exoplanetesimal material. And this is because if you just look at, for example, how many stars in our galaxy are less than 8 solar masses due to the initial mass function, we actually get something like 97% of stars in the galaxy, in the Milky Way galaxy, will actually eventually end their lives as a white dwarf. And so if you're a stellar astrophysicist person, you want to understand white dwarfs because that's the sort of end stage of most stars in our galaxy. If you're an exoplanet person, you want to know what happens to these exoplanetesimals around white dwarfs, because once again, most of the stars will eventually turn into white dwarfs. So if you have exoplanets around these low to medium mass main sequence stars, you'll eventually have maybe planetesimals around white dwarfs. Okay. So a little bit more information about just white dwarfs in general. And so there's a few different categorizations of white dwarfs, but typically we think of white dwarfs as made up of a core that is mainly carbon and or oxygen, and then an atmosphere around the white dwarf that is mainly made up of hydrogen and or helium. And so if you imagine if you think of this type of system and you observe it with a spectrograph and you get a spectrum of a white dwarf, you should see something like this. So this is specifically for, the resolution is not great here, but this is specifically for a hydrogen white dwarf or a DA type white dwarf. What you see here are just the hydrogen lines. And so you shouldn't really expect any other elements to be present in this spectrum. And so in comparison to that, if you look at something like the sun, obviously the sun is has a lot of different elements in the atmosphere, and so you see a lot more lines here. Another thing you can note here is that the white dwarf, if you see each of these spectral lines, they're actually gravitationally widened due to the fact that the surface gravity of the white dwarf is actually quite strong. So white dwarfs are really, really dense objects, and due to that, you see these sort of broadened lines. But once again, you should see hydrogen and or helium and not much else. In comparison, if you go out and actually observe these white dwarfs, what you see is that you actually see this sort of metal pollution or heavier metal elements that we don't necessarily expect to see on the surface or the atmosphere of a white dwarf. And so here, in addition to things like hydrogen, helium, and oxygen, you were actually seeing really heavy metal elements like magnesium, silicon, carbon, calcium, etc. And so you see a sort of wide variety of metal pollution happening on white dwarfs. And statistically, this is something like a quarter to half of white dwarfs that we observe have these metal pollution signatures that we observe on the atmospheres through observing their spectra. And so this is definitely, a substantial fraction of white dwarfs that we see metal pollution on its surface when we don't necessarily expect that to be the case. And so a second reason why we don't expect these heavier elements is one thing that I mentioned already, which is the high surface gravity of white dwarfs. And so what happens is if you just sort of pollute this white dwarf with heavier metal elements, because of this high surface gravity, the heavier atoms are going to very quickly sink toward the core. And so eventually you'll once again get this differentiated structure where all of the heavier elements sink towards the core. And once again, you only see hydrogen or helium on the atmosphere. And so to explain this sort of metal pollution signature, what we need is an active accretion event. And so something like a planetary debris that's just been disrupted and we're now polluting the white dwarf's atmosphere actively with this sort of exoplanets, planetesimal metal elements is sort of the picture that we have currently. And what I want to mention about these white dwarfs is that you can actually sort of flip this logic and use metal pollution signatures that we observe on white dwarfs to study exoplanet compositions, specifically bulk compositions, that is. And so here I'm showing the mass fraction for a variety of different systems. So you have Earth, so this is bulk Earth on the far left here, and the comet Halley right next to it. And then all of the other ones that are listed here are exoplanetesimal bulk compositions that are inferred from polluted white dwarfs. And so we can actually, and there's, this is a little bit older now. So now we're actually starting to catch a little bit more of the icy material and things like that. But at the time of the publication of this paper, what we actually saw was that most of the polluted white dwarf signatures that we see are actually bulk Earth-like. And so if you can somehow, for example, disrupt an Earth-like planet, you might be able to explain the relative compositions that are observed on these white dwarfs. And so once again, we're starting to see these ices and things like that. And so there's still uncertainties here. But the point here is that we can actually use this to start studying exoplanetesimal bulk compositions that we wouldn't otherwise be able to study. Okay, and so like I mentioned, I'm a dynamicist, and so I'm curious as to how you get these exoplanetesimals to sort of tumble into the white dwarf. And so specifically, when you talk about trying to disrupt these planetesimals onto the white dwarf, what I mean by that is something called a tidal disruption event, which means that if you have some sort of asteroid or comet, the asteroid or comet is going to approach the white dwarf at such a close distance that the tidal gravity, so meaning the gravity on one side of the asteroid is much stronger than the gravity on the other side of the asteroid, and it gets ripped apart. And now you have this sort of debris disk from which the white dwarf is actively eating it, because now the asteroid is not one piece of rock, but now it's sort of a bunch of pebbles sort of kind of being accreted onto the white dwarf. And so the equation that describes this process of when the tidal gravity of the white dwarf overcomes the self-gravity of the asteroid is something called the Roche radius. And so that Roche radius is roughly 1 solar radius for a white dwarf. And so I forgot to mention right at the beginning, but a white dwarf is, if you imagine shoving roughly a solar mass star into something like the size of Earth, that would be something that's close to a white dwarf in density. And so if you imagine you have an Earth-sized object with a solar mass, shoved into it, And now you have a radius around it of 1 solar radius, to which you have to sort of torque these asteroids and comets into to get a tidal disruption event to happen, and for the white dwarf to accrete these planetesimals. Okay, and so in terms of dynamics, what that means is that the asteroid or comet orbit has to be really eccentric. And so here, what I'm illustrating is if you have the same semi-major axis orbit of an asteroid or comet, and you just mess around with the eccentricity, what you find is that as you go from a circular orbit with an eccentricity of 0 all the way to a high eccentricity orbit of 0.9, the closest distance of approach, which is called the periapsis distance, gets closer to the white dwarf. And so you start to create these high eccentricity orbits, and now the asteroid or comet is sort of in the danger zone of getting tidally disrupted. Okay, so in terms of equation, you can write the periapsis distance like this. So 1 minus the eccentricity times the semi-major axis. So once again, as E approaches 1, you get the periapsis distance that goes to 0, and eventually within the tidal disruption radius. So exactly how eccentric does the orbit need to be? And so I'll come back to why we're specifically looking at something like the Kuiper Belt in a second. But if we, for example, take the Kuiper Belt, for instance, the Kuiper Belt semi-major axis is roughly 40 AU. So if we take 40 AU to be the semi-major axis, the eccentricity that we need this Kuiper Belt object to be in is something like 0.9999. So we need to really drive these eccentricities up in order for these tidal disruption events to happen. Okay, and so I'm not the first person to start thinking about this problem. And so I wanted to sort of walk through a few of the various different ways that you can get these extreme eccentricities. And so, so the problem is basically you have a white dwarf and you have a piece of rock. How do you get that rock to become an eccentric, super eccentric orbit? One study showed that basically if you get orbital resonances between something like a giant planet that might exist at these distances, you can get these extreme eccentricities. You can also have a binary star companion. So essentially you have 2 massive objects and you have these 3-body encounters that you can use to get these asteroids to enter the white dwarf. You can also have instabilities triggered by planetary engulfment. So planetary engulfment is something that happens during the giant phase. So you might be familiar with this idea. It's pretty popular in sort of the layman's science, if you will. The idea that the sun is eventually going to be a giant and will probably engulf most of the inner solar system planets. That can actually trigger these dynamical instabilities that can get these planetesimals or planets to be eaten by the white dwarf. And this is something that I'll come back to in a second, but the very last stage of this giant phase is actually losing mass. So this outer layers of the stars are being lost in the surroundings. And this sort of mass loss can also trigger these scattering events of planetesimals into the white dwarf. A couple more for you. So you can actually get, people have thought of different sources of these planetesimal pollution as well. So I'll talk about planetesimals or smaller bodies in the solar system today, but people have thought about eating entire planets or maybe even exomoons. So there are some sort of exotic dynamics related ideas out there as far as how you get these pollutants to enter the white dwarf. Now, one sort of issue that we run into, and so this is just basically a histogram of polluted white dwarfs as a function of the effective temperature of the white dwarf. And so what you see is that as the white dwarf cools, we call this the white dwarf cooling age, but you can actually start to back out roughly how old the white dwarf is. And so how long has it been since the white dwarf was born with a given temperature? And when you look at this histogram, as you can see from these notches at the very top here, these are some really old white dwarfs that we're seeing, that are metal polluted by these really heavy elements. And so this sort of poses a problem because if you look back at the previous slide, a lot of the mechanisms were invoking things in the giant phase or the mass loss and things like that. And it's a little bit, I guess, ironic because I am invoking the kick today, but I'll show you that the pollution signal is actually long-lived from that type of dynamical mechanism. So the problem is that a lot of the mechanisms that people have invoked so far actually struggle to get these really old white dwarfs that are polluted. And so the big question that I want to try to begin to answer today, and so I'm trying to convince you that the solution that I came up with is one of the possible solutions to explain this problem of how do we get white dwarfs to tidally disrupt asteroids and comets many millions of years to even a billion years after the formation of the white dwarf. Okay, and so before I get into the details, these are sort of jargon that dynamicists like to use that I wanted to familiarize yourself with. So if you imagine a eccentric orbit of a rock around the white dwarf, so words that I've probably already thrown around. So apoapsis is this point here, the farthest point that the piece of rock will reach along its orbit. The periapsis is, on the other hand, the closest distance of approach that the asteroid will reach along its orbit. Something that dynamicists like to use is vectors to try to define this eccentric orbit. And so one vector you're probably already familiar with. And so if this piece of rock is orbiting this way, the angular momentum vector is out of the board. And so specifically, we calculate angular momentum vector as sort of a specific angular momentum vector, which is just the angular momentum vector per unit mass. This will pop up again, but J we calculate as r cross b. So if you know the position vector and the velocity vector, you can calculate the angular momentum of the orbit. And what this tells us is basically what plane the orbit is in. And so one other vector quantity that we like to use is something called the eccentricity vector. I know that Hayden is familiar with this, but the eccentricity vector is also something that you can calculate from just the position and velocity and the angular momentum vector. But the important thing to note is that the magnitude of this eccentricity vector is going to tell you how elongated that orbit is. So it's just equal to the scalar eccentricity. So for a circular orbit, it's a 0 vector. And for an eccentric orbit, it's whatever the eccentricity of that orbit is. And the direction is always going to point from the apoapsis to the periapsis of an orbit. And so put together with the angular momentum vector, which is going to define this plane, the eccentricity vector is going to tell you basically the direction of that elongation in that plane. And so you can combine the two to describe an orbit uniquely in 3D space. Okay, with that, what I want to talk about today is specifically white dwarf kicks, which is something that is given to the white dwarf when it's born, and how that specifically affects the orbits of the planetesimals around it and the subsequent evolution of these asteroids and comets. And so I'm using the Ring Nebula here as just an illustration purpose, not necessarily for a scientific accuracy here. But if you imagine at the very center of the Ring Nebula is a white dwarf, and what we're talking about here is this mass loss that happens during the asymptotic giant branch. And so there's a suggestion that perhaps this mass loss doesn't occur equally in all directions. In other words, the mass loss is not isotropic. And so when you have anisotropic mass loss, what happens is that obviously more mass is shot up in one direction over the other. And so the white dwarf actually needs to receive a kick in the opposite direction to balance the linear momentum of the system. And so white dwarf natal kicks are typically thought to be about 1 to 3 kilometers per second. And what I want to mention is that this sort of number of 1 to 3 kilometers per second is actually coming from more sort of dynamical studies of white dwarfs. And so if you look at clusters, like this is a globular cluster, for example, and the distribution of the white dwarf that exists in the cluster, you can say that you can see that actually the white dwarf distribution is a little bit more extended than we expect from dynamics. And one way to explain that would be to give the white dwarf a kick of 1 to 3 kilometers per second when it's born. And so therefore it becomes a more radially extended distribution. This second reference here is actually looking at wide binaries in Gaia, for example. It's also fairly consistent with this number of 1 to 3 kilometers per second. But mainly, once again, where we think the natal kick is coming from is this stellar evolution picture. But how we know that the white dwarf kick needs to be there is through actually observing these white dwarfs in space in terms of position. Okay, great. And so this is a toy model picture of how we can start to form these eccentric disks or structures of asteroids and comets around this white dwarf that is not quite isotropic. And so I want to walk through this toy model example that I did a few years ago because I think it's nice to have an intuitive idea of where this eccentric disk comes from. And so let's treat the screen as the XY plane here. And let's imagine an asteroid orbit that is just a circle around the white dwarf. And let's just say that the white dwarf, the asteroid is actually rotating in this direction, so angular momentum is once again out of the board. And you have a kick. In this situation, let's say that it's in the plane of the disk in the positive x direction. Okay, so there are two simple cases that you can figure out what happens to this planetesimal orbit over time. And so if you imagine this green planetesimal is on the circular orbit, And then now the green planetesimal is located there when the kick happens. And so the green planetesimal is actually, pointing, the velocity vector is initially pointing in the negative x direction, but because of the kick, once again, the white dwarf is much more massive than the planetesimals, and it's starting to get a boost in this direction. And so in the reference frame of the white dwarf, the planetesimal actually seems to speed up in the opposite direction. And so this boost is actually going to throw the white dwarf, the planetesimal, into a larger eccentric orbit, as shown in the green. And you can repeat the same exercise with, let's say, this blue planetesimal that's located down here. Sort of the opposite happens. So initially, the velocity vector is pointing in the positive x direction, but now the white dwarf gets a kick in the same direction. And so in the reference frame of the white dwarf, it seems to actually slow down, and it's going to fall into a smaller eccentric orbit, shown in the blue here. And so this was the first sort of toy model exercise that I went through to figure out that basically the eccentricity vectors of these post-kick orbits have some sort of preferential direction. So in this case, the kick was in the positive x direction, and a lot of these post-kick orbits are actually going to point in the y direction. And so you can actually repeat this exercise. So one kind of quick aside that I wanted to mention that I figured out was kind of neat is that this sort of giving boosts to things is very analogous to something called the home and transfer orbit. So this is if you have a satellite and you want to send the satellite to, for example, Mars or something like that, then Earth is roughly on a circular orbit and Mars is on a larger circular orbit. And the most fuel efficient way to get to Mars is actually something called the home and transfer orbit, which is where you sort of give a boost to the satellite parallel to the direction of motion. And you actually take yourself to an eccentric orbit, which is shown in this like sort of half of an ellipse, this red orbit here. And then you give another boost, and then that'll take you into this larger circular orbit. And so now if you imagine if you're an asteroid or comet around a white dwarf, what's happening is the white dwarf is actually the one that's getting a kick. But in the reference frame of the white dwarf, all of the asteroids and comets are starting to get a boost in the opposite direction. And because of this, you actually get a whole bunch of these sort of home and transfer orbit-like eccentric orbits around this white dwarf. And so you can repeat the same exercise that we did. So we only looked at two simple cases, but now if you imagine you have a bunch of, you have a disk of planetesimals, and you have asteroids and comets that can be located at any point in that disk. And it's initially an axisymmetric disk. And you can calculate that the expectation is that if you, for example, kick this system of circular orbits in the positive x direction, you get an eccentric disk, like what's shown here, where basically preferentially, all of the orbits are going to gain eccentricities in that direction, and therefore have these eccentric orbits that are all aligned in one direction. So you have this sort of a periapses all kind of congregated in this region, and apoapses on the other side. Okay, awesome. And so one thing that I wanted to mention is obviously that was the analytic expectation. Now we're trying to verify it with n-body simulations. We typically use this code called rebound for direct n-body simulations. And so the first kind of thing that we did was to try to figure out how likely this is. So one key assumption that I made in the previous exercise was that the kick was in the plane of the disk, right? And in general, if we say that the anisotropy of the star has nothing to do with the disk orientation, then there's no reason to assume that the kick is going to be in the plane or out of the plane of the disk. So the first study that we did was to look at this kick angle. And so this is kind of a simple geometric exercise that you can do, but if you have a sort of a plane in 3D space and a random vector in 3D space, it turns out that you're more likely to get an in-plane kick than an out-of-plane kick. And so this is what this histogram is showing you here. And so this middle bar here is what corresponds to an in-plane kick. Where sort of the inclination between the angular momentum vector and the kick vector is 90 degrees here. And so, hi.
Sorry,
No worries.
just a basic question, but you're implying that the mass loss from the white dwarf would be asymmetric.
Mhm.
What are some of the physical reasons that make it asymmetric?
Yeah, so I think the stellar modeling side is still very uncertain at the moment. But there have been suggestions that, for example, this is a cool idea that came out recently that I liked, which is that in the giant branch phase, you have engulfments of planets, and those can actually sort of pollute the giant phase of the planet. and therefore result in anisotropy when the outer layers start to become lost. And so these are kind of similar to the instabilities triggered by planetary engulfment idea that I mentioned.
So compositional asymmetry.
Yeah, compositional asymmetry would be that case if you, for example, engulfed a planet, right, which is a substantial amount of mass, and dump it sort of on the surface of the white dwarf before it goes, starts to lose mass. You can drive anisotropies that way. There have been, I think, other suggestions related to the spin of the star, for example, but I don't know that study too well. But yeah, those are some of the stellar side of things. But I think the kick, 1 to 3 kilometer per second, that magnitude is purely coming from looking at the distribution of white dwarfs. Yeah. Okay, awesome. And so basically, this is just to say that in-plane kicks are probably more likely. And so in this particular study, we focused on just in-plane kicks and looking at the asymmetries that you can drive due to these in-plane kicks. And so now what I want to show you here is that in these n-body simulations, you have, initially what we were assuming is a circular disk, so sort of circular rings of asteroids and planetesimals. We distribute it. And these are direct n-body simulations, so we know exactly where the asteroid and comet are. But here, I'm just showing you the instantaneous Keplerian orbit. So obviously the white dwarf dominates the gravitational field in the system. And so you can kind of draw an instantaneous ellipse that's associated with each of these asteroids and comets. And so after the kick, you form this eccentric disk, and you're going to see this sort of eccentric disk evolve over time. And you are probably wondering about the prograde retrograde thing. I have a few slides about that at the end. But for now, what I want you to notice is that, so the kick forms this eccentric disk, and as you see this eccentric disk evolve over time, something peculiar is happening here. So for one thing, these larger eccentric orbits, they sort of break off from the rest of the disk and do their own thing. This is something, you expect from n-body simulation. So depending on the eccentricity, depending on the semi-major axis of the asteroid or comet, you're going to precess at a different rate. But actually, the bulk of the eccentric disk is actually able to stay together. So this dark shaded region, that's this sort of eccentric orbit, sort of, coherently precessed in the prograde direction in this situation. Okay, so what's going on here? And so to explain what's going on, what I did in this movie here is, so once you form an eccentric disk, you can kind of think of an average eccentric orbit that exists in the disk. That's something that I'm illustrating here in the thicker white line. The red orbit is if you imagine just plucking one asteroid or comet from the n-body simulation and sort of seeing how that one individual eccentric orbit interacts with the rest of the eccentric disk. And so what you see in n-body simulations is something like this, where you have this eccentric disk that is, we're treating as one mean eccentric orbit. It's precessing, like I said, coherently in the prograde direction. As it does that, the red orbit, which is this individual asteroid or comet, is going through these oscillations about the rest of the eccentric disk. And the reason is actually as simple as Kepler's second law. So if you imagine the asteroid or comet, they all have the same periapsis and same apoapsis. What happens is that the asteroid or comet they're going to whip around, the periapsis, and they're going to slow down as it approaches apoapsis. And so what happens is if you're an individual asteroid or comet and you're just like a tiny mass in the system, you see the rest of the asteroid comet population sort of as a massive collective particle. And so if you imagine all of the asteroid or comet are whipping around here and they're slowing down as it approaches apoapsis, so you actually have this average mass that is located closer to the apoapsis of these eccentric orbits, and therefore this individual asteroid or comet always gets torqued back. It's sort of forced to rejoin the eccentric disk every time. And this torque mechanism actually does a consequence of this is the eccentricity oscillations that you see in the red orbit. And so if you see these coherent torques, what happens is as soon as the red orbit starts to lead, it's going to get torqued back. And due to this angular momentum exchange, the red orbit actually needs to become more eccentric. And on the other hand, when it lags the rest of the eccentric disk, it has to circularize and speed up its precession to catch up to the rest of the eccentric disk. And so once again, it's doing this sort of oscillatory behavior, and it's also going through these eccentricity oscillations where they become more eccentric and then more circular, more eccentric and more circular. Okay, and so this eccentricity oscillation is really what's driving the tidal disruption events in our simulation. And so let's focus on the first panel for now. This is time in millions of years on the x-axis here. And on the y-axis, I'm showing you the fraction of the planetesimal debris disk that gets tidally disrupted over time. And so what you see here is that planetesimals are getting tidally disrupted, and about 15% of the disk that initially formed is disrupted within 120 megayears in this case. And why is that? Well, it's because of the eccentricity oscillations that I talked about in the previous slide. And so here, I'm showing 1 minus the eccentricity. So I'm showing 1 minus the eccentricity because 1 minus E is proportional to the periapsis distance. So the planetesimals are getting closer to the white dwarf as you go downward in the plot here. And these are examples of planetesimals that we detect as a tidal disruption event in our simulations. And what you see here is that all of these, if you just pick a color and just follow it along, you see these eccentricity oscillations that I was talking about that's happening to each of these asteroids until it finally reaches this tidal disruption radius of about 1 solar radius that I was talking about. Okay. And then finally, just to show the fact that the eccentric disk is stable due to this mechanism. This is the average eccentricity vector I'm plotting on the y-axis over time. And so what you see is that the kick, aligns these orbits in this nice eccentric disk. And as the eccentric disk precesses, it can actually stay together pretty well. And so an axisymmetric disk would have this average eccentricity vector of 0 because there's no preferential alignment of the vectors. If you have an eccentric disk, you get something that's closer to 1 or whatever the mean eccentricity of the system is. Okay, so the picture is basically that there's an eccentricity alignment that can hold itself together for a while, and therefore you get these eccentricity oscillations that result in these tidal disruption events of asteroids and comets. Okay, and so what I wanted to mention is that if you, once again, a key assumption that we have to make here is how massive the disk is. In this case, we assume, I believe, 1 Earth mass or so. And the number that we get is something like 10 to the 12 grams per second mass accretion rate from these TDE rates, which are roughly consistent with the highest observed accretion rates that we see from white dwarfs. So typical rates are something closer to 10 to the 8, 10 to the 9, but the highest observed rate that I can find in the literature is about 10 to the 12. And so 1 Earth mass eccentric disk is able to explain that level of mass accretion. Okay, I'm good on time, I'm assuming. Okay. So the Prograde retrograde that was happening in the movie, I wanted to explain where that was coming from. And so now if you imagine you just populated this initial disk with a bunch of circular orbits, what I talked about here of, you either lose speed or gain speed depending on where you are in the orbit. If you imagine now sort of zooming out and looking at a larger circular orbit, what can happen is that because these orbits that are farther away from the white dwarf at the time of the kick are moving slower, they're actually, they can be flipped on its orbit, right? And so if you imagine, for example, this orange planetesimal now that is initially located down here, maybe its circular speed, right, is actually lower than the kick speed. And so the kick is actually able to completely flip the direction of orbit of the orange planetesimal. And so the orange planetesimal gets flipped by the kick, and it's going to enter this eccentric orbit, once again, aligned in the same direction. But now the orange planetesimal is actually on an eccentric orbit that is in the reverse orientation with respect to its original orbit, right? And so once again, this is a little bit harder to imagine because the white dwarf is the one that's getting a kick. But if you imagine, this is kind of like the classic example, I guess, of a car that's passing you on the highway. What happens is that you seem to be actually going in the opposite direction with respect to the car that's passing you. And so the white dwarf starts to get a boost, but that boost speed is actually faster than the speed at which you were orbiting initially. And so you're still bound to the white dwarf, but you start to orbit in the opposite direction as the white dwarf gets this boost. Okay, and so if you put that all together, you get this sort of complicated plot here. And so what I want to first explain is that the color bar on the top, so let's ignore the bottom panel for now, focus on the top panel. The top panel has this color bar that is just the eccentricity vector y component. And so you can see here that the y component of the eccentricity vector is sort of coherently in the positive direction. So all of this blue here is are eccentric orbits that are pointing upward. What happens is at the very tail end, at very large semi-major axes, you can actually flip these completely. So you can get these really large eccentric orbits that are actually pointing the other way. But a majority of the disk is actually pointing upward. So just like I said, there's alignment of the eccentricity vectors there. And on the y-axis here, I'm showing the z component of the angular momentum. So this is with respect to the original angular momentum. So if you're prograde, you have a positive jz. And if you're retrograde, you have a negative jz. Finally, this is a function of the semi-major axis. But what I want to mention is that I normalized the z component of the angular momentum so that you actually get more circular orbits farther away from this central line. So if you have a circular orbit, you have more angular momentum. If you have a really radial orbit, you have no angular momentum. And so you get these really high eccentricity orbits that are closer to this black dashed line, and you have circular orbits that are either here or here, depending on whether you're prograde or retrograde. Does that, there's a lot going on here, but does that make sense to everybody? Okay, great. And so what's happening here is that, let's say, so starting at low semi-major axes, here you are, let's say, something like Earth. So if you're orbiting at 1 AU, your orbital speed, which is about 30 kilometers per second, is that right? Okay, great. That is actually much, much faster than the kick speed, which is expected to be 1 to 3 kilometers per second. And therefore, you don't care. You're still doing the same roughly circular orbit that you were doing before. As you get to a region of space, so here you're starting to get into the hundreds of AU, so really far out from the white dwarf, your speed starts to become comparable to this kick of 1 to 3 kilometers per second. And therefore, your orbits become more eccentric and aligned, as shown here. So you get from more circular orbits to more eccentric orbits. And then finally, you get to a point where all of the planetesimals start to actually get flipped into the opposite direction, and you see this sort of retrograde population start to populate the disk in the outskirts. Yeah.
So the semi-major axis is the original semi-major axis or the final?
This is the final. Yeah.
Okay, so where did they all started out at? Where did your initial body start out at 40 AU?
So let me think about this. So yeah, in the one, these are all starting at up to less than Oort cloud distances. So the initial disk is like here.
Okay.
And then these bodies that are farther away than 1000 AU are being tossed out farther than where they started.
Okay.
But actually, if you look at one circular ring, that circular ring can change dramatically in semi-major axis depending on where the planetesimal is. So you can either get a boost, right, which is going to throw you into a larger semi-major axis, or you can fall into a smaller semi-major axis orbit. And so you have the initial semi-major axis range, which actually doesn't map sort of one-to-one with the final semi-major axis range. But this is the final semi-major axis range. So you see these like large retrograde orbits that are like tossed out to really far distances. And you see this eccentric disk that is starting out at circular orbits initially, but you can either get scattered in or scattered out, depending on the position of the asteroid. Okay, so in terms of, if you just kind of directly map this to our solar system, just to orient ourselves, the Kuiper Belt is roughly located at 40 AU, and you have Oort cloud kind of starting at maybe 2000 AU or so. And then finally, you have this region in between that's called the scattered disk, where Neptune is sort of scattering out these smaller bodies and delivering them to higher and higher semi-major axes. And so basically, the picture is that anything from this mechanism, anything within the Kuiper Belt are not affected largely. And so you have these larger semi-major axis orbits that are maybe populating the scattered disk or the Oort cloud that are the most affected by this kick. Okay. And so one prediction, so if I return here, there's a significant number of retrograde planetesimals that I talked about. And so one thing that is cool that you find in these n-body simulations is that a lot of these tidal disruption events that I'm talking about, so the asteroids actually getting tidally disrupted by the white dwarf, a lot of them actually happen in the retrograde orientation. And so what that means is that you have, if you imagine a planetesimal debris disk that is rotating or orbiting in the same direction as the white dwarf is spinning, you actually have 40% of these tidal disruption events that are actually happening in the opposite direction. And so we have a prediction about the circumstellar environment of white dwarfs. So when you have a metal polluted white dwarf, about 40% of them we expect from this mechanism are actually in the retrograde orientation. So they have debris disks that are rotating or orbiting the white dwarf in the opposite direction. And so I would love to talk to observers about whether this can result in something that's observable to test our mechanism, things like that. Okay, great. So what's next? I think actually did end up filling the 45 minutes. This is great. Yeah, what am I thinking about next? And so the first thing is the fact that I only looked at circular disks so far. But if you look at our outer solar system, for example, so something I mentioned is the scattered disk. The scattered disk is not circular because they're being scattered out by Neptune, and therefore they're actually on eccentric orbits. And so this is the outer solar system, semi-major axis eccentricity. What you see is this sort of complicated structure of circular and eccentric orbits kind of all put together. And in particular, I'm also curious because this scattered disk is primarily created by Neptune, which is a giant planet. And a giant planet itself could exist, in this region that we're talking about in exoplanet systems. And so with the presence of a giant planet, does the dynamics that we're talking about here change at all? Because the eccentric disk really relies on the self-gravity of the system. And so here we didn't invoke any planets at all. This is just the self-gravity of the small bodies in the exoplanet. But what if we had a giant planet that's creating this sort of eccentricity in the outer solar system? And then the second thing is returning to this picture of exoplanet compositions. What does our mechanism mean in terms of exoplanet composition? So one thing that I've thought about is the fact that we're primarily talking about outer solar system objects. And so we might expect that we are predicting a larger icy content of exoplanetesimals that we're disrupting from our mechanism, as opposed to maybe other dynamical mechanisms that are disrupting other planetesimals from other parts of the solar system. And then finally, people have actually shown that you can actually create these, this is a picture of Oumuamua here, and you can create these Oumuamua-like interstellar objects due to the disruption of a planetesimal by a white dwarf, which is kind of a neat idea. And so I also wanted to try to, kind of relate this process to not just what's happening in terms of the accretion, but also what's happening to, kind of debris that sort of fly off into interstellar space as a result of this disruption event. Okay, so I will end there. And if you're curious, this is the QR code that points to our paper that discusses this mechanism. And I've propped up a few images to sort of jog your memory as you come up with questions and discussion. And so thank you so much for having me.
Are there any questions for the speaker in the room?
So you mentioned in terms of the alignment of the kick and the disc, obviously it's most efficient if your kick is exactly in the plane of the disc, but I assume there's some intermediate regime where it doesn't have to be exactly aligned. Like how close does it have to be to still get an eccentric?
Yeah, so the fraction that we end up with is about 80%. So I actually don't know what that corresponds to in terms of angle. Mm-hmm. But basically, you're absolutely right. So what we need is a significant enough in-plane component of the kick. So yeah, any kick is gonna decompose into in-plane and out of plane. And if you have too much of an out-of-plane component and not much of an in-plane component, like you suggest, you basically don't get this sort of lopsidedness because you have axisymmetry and you're kicking in that axis. So you don't get this lopsidedness. But you get this lopsidedness that is significant statistically at about 80% of the time, assuming you don't know anything about the kick direction though. So that could also be, could change as people are studying, doing detailed modeling of stellar evolution. But yeah, great question.
Everett Schlauwen has a question online. Excellent talk. How much does the rate of tidal disruption events depend on the mass of the disk?
Yeah, great question. So I hope I'm not lying. So when I said 1 Earth mass, I said 10 to the 12, right? I said 10 to the 12 grams per second. So the TDE rate / accretion rate is the dependence on it is the mass of the disk squared, or to the -2, I mean. And the reason for that is because once you have to first of all assume that's the reservoir, right? So you get one, obviously, if you assume a more massive disk, you can get more mass accretion per tidal disruption event rate. And so you get one dependence that way. And the other reason is that the precession rate of the eccentric disk actually depends linearly on the mass of the disk as well. So all of that is to say, sorry, that's dynamicist talking. Okay. So if you have a 1 Earth mass disk, it was 10 to the 12. If you reduce that to something like 0.1 Earth masses, so if you lower it by an order of magnitude, then the mass accretion rate would decrease by 2 orders of magnitude. So you would expect about 10 to the 10 grams per second. So to reproduce typical rates, that's like maybe 10 to the 9 or something like that, you can get away with maybe a fraction of an Earth mass. And so, yeah, we can debate about, whether we should see that much mass in the outer solar system or not. But that's kind of what we're looking at in terms of accretion rates.
Don McCarthy would like to know, Everett says thank you. Don McCarthy would like to know, can a white dwarf's magnetic field play a role in the rate of differentiation?
I think so. I am definitely not the expert on that. But I think the numbers that I've heard is that, for example, if you have a hydrogen white dwarf versus a helium white dwarf, that actually changes the timescale of differentiation. So a helium white dwarf, you're looking at something like maybe a couple of millions of years, couple of mega years. So you're looking at an average accretion rate over the last maybe 1 mega year or 2 mega years. Whereas a hydrogen white dwarf, the differentiation timescale is very short. So you really need an active accretion event to be ongoing. So it's kind of like you measured the instantaneous accretion rate. I don't know if I actually don't know if probably the question asker has a better idea of this, but whether that can change the, in what direction changes the differentiation timescale. I'm not quite sure.
I'm sure Don has more to say on that.
Yeah.
Are there any more questions in the room? Real quick, John?
So 2 questions. In your plot with that shows the TDEs,
Yeah.
colorful, yeah. I think it went up to 120 million years, and then will we just extend it out to a gigayear to explain the pollution in the oldest white dwarfs? Is that how it works?
So yes, so this is computation time limited.
Yep.
So you can definitely extend it. One reason that I didn't want to extend this particular simulation run is because we were using a lower number of planetesimals than we would we actually can't ever use a realistic number of planetesimals in direct n-body simulations. But basically in n-body simulations, what we do is we bump up the number of planetesimals we're using until we start to see some sort of convergence in behavior. And we are kind of treating each particle as a collection of planetesimals in that situation, because we can't obviously simulate tiny, down to tiny particles. But one issue that we run into for a small number of planetesimals is relaxation. So basically the planetesimals are going to very efficiently scatter each other because we're treating them as one big collection of planetesimals rather than something that's more realistic. And so you actually, in this simulation run specifically, you actually start to run into that relaxation timescale barrier at about 120 mega years.
But basically, you're expecting your mechanism to work.
Absolutely, yeah.
Yeah, okay.
But yeah, to be able to show it clearly is kind of, what I'm talking about now
Sure.
and babbling about, is that to extend it to 1 gigayear, I need to use about, an order of magnitude more planetesimals. Here, I think I'm using 10 to the 4, so I would have to use something like 10 to the 5.
Okay.
Which might be a little bit tricky, but
Fine.
you would expect it to be the same.
I accept that. But my other question is, if you look at protoplanetary disks, so the original population of planetesimals, they are pretty small, like maybe 100 AU in the solid, 50 to 100 AU. But you want them to actually end up, you need things to be kind of more extended to get these great effects to happen.
Yeah.
So if I understood the later part of your talk, it sounds like having Neptunes and things like that to produce that thing might be very important. Do you agree, or?
I think so. Can you repeat the first part of your question? Was about
So
the
if you
semi-major axis range?
If you look at protoplanetary disks, the disks sort of like before or when planets are forming, the millimeter sizes are pretty small.
Oh, I see what you're saying. Okay,
They're only
gotcha.
50 to 100 AU in size. They're not 1,000 AU. But you kind of need them to be pretty extended in order to get this effect. So like you mentioned, having Neptunes and things like that to do the scattering could be important.
Yes,
Of
yeah.
course, that there's an efficiency factor in how much it gets scattered, et cetera, but do you need, I guess, do you need those kinds of things? That would be quite interesting.
Yeah, I completely agree. So obviously, one thing is that Neptune or any sort of giant planet that's doing the scattering can change your density distribution. And if we don't, for example, expect the initial distribution of planetesimals to extend beyond 100 or maybe a few hundred AU, and we need this, depending on the kick magnitude, once again, you need the orbital speed to match up with the kick speed. And so if the kick speed is like 1 kilometer per second, you need this sort of radially, extended distribution. And a giant planet can absolutely help with that. And so I think the final thing that I mentioned in terms of future work is really important, right? Because you actually, in the case that you're invoking a giant planet to do the scattering to get the planetesimals to a radially extended region, then you have to take into account eccentricities initially.
Yeah.
So you would expect something like a scatter disk, which is absolutely eccentric and not circular, rather than the initial conditions that we used here, which is just a circular disk that extends outward.
Renu Malhotra wants to know, white dwarf kicks likely have some finite time over which they occur. What is the range of this time scale, and can you say how your models would be affected by this?
Yeah, so that's a great question. And so we actually don't know a ton about the mass loss time scale. So you can say that it maybe extends to the entire AGB phase, or it could be pulsed in the sense that it can be like a whole bunch of mass that's lost at once and then more impulsive. So in this work, we actually assume that it's impulsive, which is not a good assumption. But we're working on a follow-up study right now, which is assuming the opposite. So if we assume an adiabatic kick, where the kick is smooth compared to the orbit, what you get is actually exactly the same behavior, it turns out. And the reason is because, the kind of goofy figure I had where you were getting a boost in one direction and getting a decrease in speed on the other side of the orbit, that can happen to one single planetesimal orbit as it's doing the circular orbit. It's sort of preferentially starting to get a slow boost in one direction and losing speed in the other direction. And you actually still end up becoming an eccentric orbit over time, even in the adiabatic kick regime, if you assume the same kick magnitude. So if you assume that a 1 kilometer per second kick is given over a really long time scale, much longer than the orbital speed, you actually get the same type of behavior. So it turns out that the eccentric disk formation doesn't necessarily depend that much on the time scale of the mass loss. Yeah, I guess that's good in a sense because we actually don't have good constraints on the mass loss time scale.
Are there any more questions in the room? Are there any more questions online? All right, well, let's go ahead and thank our speaker again. And as I said in the email, Tatsuya will be here all week. So if you want to sign up to meet with him.
Oh yeah, I should have mentioned that. So thank you.
If you would like to sign up to meet with him, that link is in the announcement email for this talk. And for those of you here in person, we will be going to lunch at an as yet undetermined location. Talk. You're welcome to join. So again,
Thank you.